Okay, let's see if I can pull this off without blowing any fuses or dropping anything in the dog's water. Okay, this is going to be showing the battery, or 9-volt bias supply potentiometer, except instead of using the 9-volt battery for this demonstration, I'm going to use the regulated L&Co precision power supply set to produce a voltage of 9 volts about. And there's the potentiometer, there's the 10 ohm series resistor with the wiper from the pot. This wire here, these wires go to the TarBaby board where the function generator normally plugs in, except I have the Hickok moving coil milliammeter calibrated now in series with that line as well. So we'll be monitoring the current on this, and then I'm also going to show the voltage drop across that current viewing resistor, and we'll look at it on the oscilloscope. Okay, so so a lot going on at this this pot here. So I've got the input power from the power supply, I've got the voltage probes from the voltmeter up there, and I've got the output wires going down to the circuit. Okay, here's the circuit that we're using right here. Alright, so instead of the battery, we've got the power supply in there. So from the positive side of the battery potentiometer combination, that goes to the point where the function generator minus connects to the circuit between the current viewing resistor and the transistor, and the wiper goes through the 10 ohm resistor to the sources of the Q2 stacks and the gate of the Q1. That's the point where the function generator plus normally connects to the rat TarBaby circuit. Okay, so that's the circuit that we're using, and I'm monitoring with the oscilloscope to prove that we're actually in the oscillation mode. I'll first monitor the common MOSFET drains from here with respect to the ground point. Then I'll disconnect that probe because we need to monitor across this current viewing resistor, and of course I can't do that with a ground hooked up over here. So this probe has to be disconnected, and then I have to hook up another probe here to monitor the current over that resistor. And then I also, of course, have the moving coil ammeter right in there too, the Hickok. Okay, so that's the setup. Alright, so let's see, right now we're looking at scope channel A, the common MOSFET drains, 50 volts per division, 10x attenuated probe, DC coupling, and there's the probe on the transistor side of the load right there, and there's its baseline, and I already have it hooked up to the battery supply. Okay, so if I unhook it, let's see if I can do this. Boom, there you go. So it drops down to baseline, I hook it up, and it goes up to battery voltage right there, 49.1 volts. My batteries are still over 12 volts each after all this demonstration. So that's 3-4 days at 12 volts each of all of this stuff. So I have just as much right to claim that my batteries are not discharging as anyone else does. However, we all know that they are. Okay, so sorry, just a second here. Let me make that solid connection. Okay, there. I don't know what you were looking at that point, but at any rate, there we are. Or no, there we aren't. Wait, what's going on here? Oh, we've come loose on the probe. Okay, so sorry. There we are. Okay, the probe is coming loose. Yeah. What a demonstration. Okay, there we are. Common MOSFET drains showing the battery voltage because the MOSFETs are off. Alright, now I'm going to go over here and start turning this pot, if I can do it without knocking things off. And we'll look at the current down here. Alright, turning pot, turning pot, turning pot, turning pot, turning pot. You can see the current starting to go up. Alright, still no oscillations. Alright, right about there, boom, did you see that jump? Right around 15 milliamps or so. Okay, that would be about 15 milliamps right about there. And here you can see as I pass that point, there are the oscillations are starting. Alright, so that's the current, say, call it 20 milliamps there. And then as I go up and up and up and up on the pot, the oscillations get bigger and bigger and bigger until, let's go to, look at the top scale up there. Let's try to, it's very, very sensitive, but let's try to hold it at about the 8 or 155 milliamps, somewhere around there. Okay, so there I've stopped adjusting the pot. We're showing a current of just under 155 milliamps. Call it 150 milliamps on the Hickok. I hope you've already watched my calibration video where I show the calibration of this instrument against Ohm's law and a known resistance. Alright, so there are our oscillations on the common MOSFET drains. Let's go ahead and crank up the time base to 1 microsecond per division. Right there. Okay, and there you see the nice oscillations. And if we use the middle 8 radical lines, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 and a half full cycles in 8 microseconds. And you should be able to do that in your head. It's just slightly over 2 megahertz, right? Okay, so anyway, that's our oscillations. Let's go back down to 0.2 milliseconds per division where we usually stay with this. Okay, so that's, I'm not going to touch any of the adjustments now. I'm just going to remove this probe from the circuit so that we can hook up the other probe. Okay, so that probe is out. I'm going to turn its channel off, and then we'll go to the other probe over here, and that's going to be the B channel, B line. So I've set the B line right at the center radical marker, right? Hope you can see, oops, it should be right at the center. Let me adjust that a little bit. Right there. Okay. And I've got the B channel set, or rather, yeah, where are we? A, B, wait a minute. Yeah, B, that's the B probe. So the B channel is set at 0.1 volts per division, and with the 10x probe that makes it 1 volt per division on the B channel. So now without disturbing things, I'm going to hook up that probe up there across the current viewing resistor. This is a 10 ohm resistor up in there. Okay, so there we're across that 10 ohm resistor with the, or it's actually 10.3 ohms is its measured value. Okay, so it's 10.3 ohm resistor. Alright, so now we're still showing over here 155 milliamps on the Hickok, and we should still be oscillating. So now I'm going to turn, now this is where the zero baseline is, so now I'll turn the channel on to DC coupling. Alright, see that jump up there? Okay, so that's the voltage drop across the current viewing resistor, and we're at 1 volt per division, so 1.6 volts, right? About 1 point, it's actually a little, the average of that broadened line is a little below 1.6 volts. Let's call it 1.55 volts, okay? So the voltage drop across the 10.3 ohm resistor is 1.55 volts, right? So current is equal to voltage divided by resistance, so 1.55 volts divided by 10.3 ohms is 150 milliamps, okay? And on this meter over here, we're showing a little bit over 155 milliamps. So that's well within measurement accuracy, and that's pretty good for just eyeballing it. Now notice that this is not an AC signal. It has some fuzz on the top, but the voltage never reverses. And if I go ahead and crank the time base up, you can see that it's a high frequency oscillation on there. but it's not in any sense of the word AC, right? Okay. Now the reason I did this with the regulated power supply instead of a battery is because, of course, with 155 milliamps current drain on the battery voltage is going to drop and the current will change and all that. But with the regulated power supply, we don't have to worry about that. We're still at just about the same voltage as we were under no load. Okay? Got that? 155 milliamps or so indicated there. 1.6 divisions at 1 volt per division. DC coupled. Ohm's law calculation using the value of the resistor. Inline meter. Thank you for watching.